Hey guys, Mr. Betts here. I'd like to talk about a method that we can use to evaluate certain types of limits. I know it's been a little while since we talked about how we would evaluate limits, and there were certain limits that really the only way we could evaluate them was by looking at numeric values of the functions near the value in question. And a French mathematician named Guillaume de L'Hopital came up with this rule. It was actually kind of used before him, but it's named after him, that allows us to evaluate some of these limits using calculus, more specifically using derivatives. So we talked about limits to define derivatives, but now we're going to use derivatives to help us evaluate certain limits. And so this is what L'Hopital's rule looks like. Essentially, it says that if we want to evaluate a limit that is a rational function, so some function divided by another function, and essentially what's happening here is f of x and g of x are both approaching zero, which means that we get 0 over 0. We've talked about before that's an indeterminate form. 0 divided by 0 doesn't really have meaning. Then we can use L'Hopital's rule to evaluate this. And the idea is we're going to replace in the limit, instead of f of x and g of x, we're going to replace those with their derivatives. So we couldn't talk about how to do this before we learned how to do derivatives because we need the derivatives to evaluate this. There is another form of L'Hopital's rule that instead of 0 over 0, the indeterminate form is going to be infinity over infinity. And infinity over infinity is another indeterminate form. It's actually, with some manipulation, equivalent to 0 over 0. And it's not important how we would do that, but this works because the 0 over 0 indeterminate form works. So to look at how we would use this, let's look at a limit that we've done before. And it's pretty easy to see that sine of x as x approaches 0 is approaching 0, and x as x approaches 0 is obviously approaching 0. So we have that indeterminate form 0 over 0. So first thing we want to do is we want to make sure that L'Hopital's rule is actually going to work. If we go back and look at this definition here, it only works if these limits are both equal to 0. So if we're going to use L'Hopital's rule, we first need to show that those limits are both 0. So the limit as x approaches 0 of sine of x is 0. The limit as x approaches 0 of x is 0. So by writing this on my paper, I'm showing that I know that this is a limit in the indeterminate form 0 over 0. And so what I can do then is I can rewrite this limit. The x value is still going to approach 0, but now instead of sine of x over x, I'm going to take the derivatives of those two. Just to be clear, we are not using the quotient rule here. I'm going to take the derivatives independently. So when we take the derivative of sine of x, that's going to be cosine of x. When we take the derivative of x, that's going to be 1. All right, and again, just to be clear, we're not saying that the derivative of this is that. We are taking the derivative of each, the numerator and the denominator, separately. At this point, we can evaluate this limit just by using substitution. So we can plug 0 in and we get cosine of 0 on top over 1 on the bottom. Cosine of 0 is 1, so we get an answer of 1. If you remember, before we evaluated this limit numerically, so we just looked at what happens to the sine of x over x as x gets closer and closer to 0. We also graphed it and looked at what happens with the graph. Now this gives us an analytical or an algebraic way of evaluating this. I want to take a moment here to show you why it works. It actually works in part because of what we talked about in the last topic with linearization. So what I'm going to do is I'm actually going to take the limit that we're trying to evaluate, and I'm going to manipulate that until we get to a limit that involves our derivatives. So we're looking at the limit as x approaches c of f of x over g of x. And remember, for L'Hopital's rule to work, f of c and g of c both need to equal 0. So I'm going to extend this a little bit here and say this is the same thing as f of x minus f of c. Remember, f of c is 0. So we're just subtracting 0, minus, and then on the bottom, I'm going to subtract g of c, so I'm subtracting 0. So I haven't changed the value of this because the f of c and g of c are both equal to 0. You may be thinking, well, we know the limit's equal to 0, but what about the value of the function? Since f prime of c and g prime of c exist, that means that the function is continuous, or the functions are continuous, and so f of c and g of c are both equal to 0 because the limits are equal to 0. Next thing I'm going to do is I'm going to multiply the top and the bottom here by 1 over x minus c. And this is an algebraic trick that you wouldn't necessarily know to do, just like when I subtracted f of c and g of c here. But I can do that because I'm multiplying top and bottom by the same thing. So this limit now becomes limit as x approaches c of f of x minus f of c over x minus c. Hopefully that expression looks familiar to you. And then in the bottom, we have g of x minus g of c over x minus c. So you may notice now that this expression right here, as x approaches c, is the derivative of f at c. So that's just the limit definition of the derivative if we're taking the limit as x approaches c. And our limit rules say that we can separate this as the limit as x approaches c of f of x. Go ahead and write it out here. Over the limit as x approaches c of g of x minus g of c over x minus c. And each of those is the definition of the derivative at the point x equals c. This looks a little bit different than the definition that I showed you. The definition looked like this. So this limit right here is equal to, lots of arrows here, I'm going to clean that up and just get rid of it. So that's equal to the limit as x approaches c of f prime of x over g prime of x. But when we evaluate that limit, as long as both of those limits exist, then we're plugging c in and we get this expression here. By keeping it in this form, then that actually tells us that we could use L'Hopital's rule again if we got 0 over 0 or infinity over infinity again. So if we use L'Hopital's rule and we get another indeterminate form, we can just keep using it until we don't get an indeterminate form.